Good afternoon. It's good to not be going to campus today. I've been outside walking some, and it's definitely been kind of chilly outside if you get in the right direction. And the snow is, of course, has been going up and down. John, you don't know that because you're in California, but it's been a spring snow kind of a day, I would say. A lot of water, not a whole lot of snow sticking, but pretty not so great out there. Unless you like snow a lot, and I'm kind of a fan of it. So I'm ready to get started. I've posted up the exams and the solutions. I've messaged you your grades or scores. I didn't have time to put everything into my scanners here at home. I'm going to try to get to that, but I just wanted to be more prepared to actually go through material, which is relevant for papers that are due tomorrow. 2 of you have turned them in already, thank you. And also new material. There'll be a new homework assignment posted. It won't be required that you work on it over break, but it will be sitting up there. It will be from chapter 4, and that is going to be coming up today as well. I in particular want to be able to go through some of the design issues that come up in Project 1, in particular filter design, which is needed to implement the Weaver modulator, a bandpass filter to keep images from entering the coherent demodulator, and then there's another low-pass filter that's needed in the demodulator. But 2 of those filters are special. One is an interpolating filter, which is a low-pass filter with upsampler, and the other one's a decimating filter, or decimator, which is the combination of a low-pass filter and a downsampler. And I'm going to try to go through that info. I think the first thing I should be taking a look at is just looking at the exam and looking at the histograms that I created. And then we'll move off into finishing off chapter 3, get started a little bit on 4, and then talk about the project. And if along the way you've got more questions on the homework, I can also get into that. If at any time the audio goes away, the video or something weird happens, please message me on Slack just so I know that there's things happening. So that's not where I want to start. That's where I was reviewing beforehand. So I'm going over here to 3, and it's pushed way up the page because we were doing some discussion with that, I think, on Tuesday. So I'm going to try to slide down here if it will let me do that. We talked about sampling theory, of course, on Tuesday. We went through some of these pulse modulation types, most of which are not all that popular anymore. Pulse width modulation is very popular in robotics and motor control, but not so much for communications. Delta modulation used to be used in analog telephony, where we wanted to digitize. Pulse code modulation is kind of where I was at when we signed off. We covered part of this. This is probably the most common, the most popular way of digitizing speech and getting it into, say, a device like a cell phone or the medium that I'm using right now to get audio sent out over a video screencast. And it's very straightforward. It involves the use of an analog to digital converter combined with the sampling operation, and then the encoding of the bits that correspond to each sample and putting those in a serial bit stream format. And we were talking about this simple figure last time, where we have a simple 3-bit encoding, and this is just showing how amplitude values are encoded into 3 bits. This is depicted as a unipolar type converter. When I say unipolar, I mean amplitude values, it would be all positive. And that's actually a pretty common PCM encoding that you find in a microcontroller. Oftentimes you have a unipolar conversion done there. Most often, the real motivation for that would be you only have a single bias supply on the microcontroller, say 3.3 volts, so you can encode analog inputs up to over a dynamic range that goes, say, from 0 almost to 3.3, the supply rail. But in most other applications involving audio, let's say, or RF, you need to have a bipolar encoding operation so that you can take signed numbers and encode them. And that's true of the demo I showed you last time in the Python software. But this is just a convenient example to show how that works. If a signal has bandwidth W, then if we have Nyquist sampling theorem for low-pass signals involved, our sampling rate has to be greater than twice the highest frequency. I kind of did a demo of that to hopefully impress upon you that equal to twice is not necessarily the greatest. Greater than is the most practical scenario. And then the textbook has this little approximation formula saying that if the pulses have width 1 over 2 times n times w, and this is based on the pulse bandwidth relationships that were talked about at the end of chapter 2, then you can approximately say that the baseband bandwidth required to transmit a PCM signal is approximately k times w times n. I would venture to say that it would probably be more along the lines of having k equaling 2, so that I'm just going to give a quick example here. If W is equal to 4 kilohertz and N is equal to 8 bits, then I'll just simply bring up my Qt console here. Not that I can't do that math if I really wanted to, because it's just 4 times 8, but I'll just do 4,000 for the bandwidth times 2 to get it up to Nyquist. So I'm sampling at greater than twice, or in this case I'm just approximating it as twice, and then each sample is encoded with 8 bits. So that gives me 64 kilobits per second of serial data that I have to stream in order to support a 4 kilohertz wide audio signal encoded with 8 bits. If we're going to put that up on a carrier, then we're going to require double the bandwidth if we're using double sideband or AM. If it was single sideband, we could get by with the 64 kilobits, but it'll be 128 if we were going to go with 8 bits on a carrier with double sideband or AM, let's say. And we'll be seeing FM can do that same thing, but FM oftentimes expands the bandwidth further. If it was binary phase shift keying, it would also be very similar to that. One of the exam questions was along those lines, and thinking of BPSK and the exam, I was going to go look at that first. I think I'm going to keep rolling on this and finish this chapter just because I don't want to be jumping around so much. So stand by for my discussion on the exam and the histogram. So BPSK would be sending, just draw this over to the side, you'd be sending pulses, and the pulses would be non-return to 0. So you might send a +1 for a 1 bit, and then you might send a -1 for a 0 bit. And the width of those is going to be proportional to the bandwidth and the number of bits per sample. So like we just talked about up here, or actually what I had expressed over here. If we need 64 kilobits per second, then over here in the picture, let's see, you get this to work again. The bit period TB is going to be on the order of 1/64K, because that corresponds to the bit rate that we need. And then if we were to draw the spectrum of this for that type of pulse shape, we're going to get a sinc function type spectrum, and the first null in the spectrum is going to be at 64. So if we say we need to send the main lobe, and remember that was part of that exam question, that main lobe, if we were putting it up on a carrier, would make the total main lobe width be double. So it would be 128 kilohertz. You might be thinking, and I'd encourage you to think this way, that if I was sending it by an analog modulation means like amplitude modulation or double sideband, I would just take 2 times W. So the bandwidth in that case, got some lag there in my pen, would be just 2 times W, which would be only 8 kilohertz. Whereas to encode it in a bit stream takes 128 kilohertz of bandwidth. I don't know, does that shock anybody, or do you just say, oh well, we can do it? The fact of the matter is, though, that's not the way it's done in cellular telephony. And in telephony, there'll be a PCM encoder to get it serialized into a bit stream, but then the information gets processed into synthetic speech using a speech vocoder, and that will compress the bit rate down considerably. And I think you can relate to that idea because you know that if you do streaming music and things like that, it is a digital scheme, but it's been compressed. Just like you know about the compression that's in a JPEG for an image, and like I was saying, the compression that's in an MP3 or something like that, or the MP4 videos that I post from lectures. And there's other things you can do in digital modulation. These are things we'll learn about in project number 2 of encoding more bits into each symbol that we transmit. Binary modulation is particularly inefficient because you only send 1 bit per pulse. I'm kind of getting way ahead of myself, but I thought that might be interesting. Okay, another aspect that comes up in this is Q, which is the number of quantization levels, is, this is wrong, it should be 2 to the n. I don't know why I've never noticed this before. Unless I'm getting my notation confused. Yeah, Q is 2 to the n, so the number of bits that we encode each sample into is n, and then the corresponding number of levels is 2 to the n. So if we make Q larger, that makes the quantization error smaller, but it also increases the transmission bandwidth. Generally, in compact disc digital audio, which is the next example up, there's 16 bits per sample, and we enjoy that when we listen to music because that gives us about 95 dB of dynamic range. But it also gives a very wide bandwidth for sending a stereo stream. So without further ado, getting into compact disc digital audio, which is a prime example of PCM that's been around since 1976, a long time now. But I'm older than that, so it's not that long. It's not as ubiquitous as it is for most of you who grew up with it being there when you were born. But PCM, in the case of compact disc audio, produces 16 bits per sample for the left channel and the right channel, and then it's framed and put into pits that are on a compact disc. So you've got a frame is composed of 27 sync bits, a subcode, data of 96 bits, so this is payload, parity of 32 bits, another payload of 96 bits, and then more parity bits of 32 bits of parity. So breaking it apart, the source bit rate, there's 2 of them, and 16 bits per channel, or per sample. So this is 2 channels, 16 bits per sample, 44.1 kilosamples per second. That makes the stream rate, the raw stream rate of just the left and right channels, 1.4112 megabits per second. With the data framing and error protection bits, that brings the total bit count per frame to 588 and a serial bit rate of 4.32 megabits per second. You might find that surprising too. It's like, how much protection do we need? Well, some of you maybe have never experienced this, but I certainly have. If you are a little bit too hard on a compact disc, it will not play properly. But it's amazing how dirty it can be and still play successfully. So that's what the extra encoding is on there for. And the synchronization has to be on there so you know where frames start and stop, so that you get the bits properly pulled apart and broken down into the individual bits. And I'll demonstrate that here in the Jupyter Notebook in a little bit. The last topic that we have in this chapter is multiplexing. And multiplexing is very common in communications. Analog is where it originally started, and last time I made comment about the sound tubes in airplanes and how you could listen to multiple audio channels that were analog multiplexed using pulse amplitude modulation. Digital multiplexing, though, is pretty much the norm today. There's multiple forms of multiplexing. We'll be looking here at time division multiplexing, and then frequency division multiplexing gets discussed a little bit in Chapter 4. So time division multiplexing, like I said, could be applied directly to an analog signal or can be accomplished at the bit level. My main interest is having it be accomplished at the bit level. There's a good discussion in here about doing it at the analog level, which still is in the book, but I find it to be somewhat confusing, and I find it to be pretty much dated, because we don't really multiplex analog signals that often anymore, or at least not that I'm involved with. So I'm planning on not giving you a problem on that, so I'm going to slip over it, but I'll gladly talk some about it if somebody wants to talk about it. Is there anybody that wants to hear a little bit more about it? Just Slack message me or say something if you've got your mic on. Okay, I'm going to keep going. So we're going to jump forward here to look at pure digital multiplexing, where we have to take the number of bits per sample which per channel then is whatever our requirement would be, and then interleave those samples. So the pictures I slipped over were showing the interleaving of analog samples, but if we interleave digital samples, it's the same idea, and it's a lot more, I don't know, a lot more precise to think in those terms. So I'm going to use this space here to kind of draw up a little example, and this is the kind of thing that I like to put on a quiz or an exam problem. So I'll just say, suppose we have 10 So we have 10 W equals 4 kilohertz speech channels, and the number of bits is going to be 8 bits per channel, and my computer is struggling, so it's not responding instantly. It's actually doing very poorly right now. So 2 high quality audio, in that case W is equal to, let's just say 20 kilohertz, and N is equal to 24, so we have 24 bits per sample, and one data stream at 10 megabits per second. So what we would visualize for a multiplexing operation, and my screen just went off. Let me see what's going on here. I just got logged out. Okay, it came back again. Is everybody still there?
I am. Yes.
Okay.
Yeah.
Did you notice my screen go black, or was it just what I was seeing that went?
Yeah. It says cameras have been turned off.
Okay. I don't know what caused that. I was rearranging my chair slightly, but I don't know. So I'm just kind of drawing this out, saying I've got, this is going to be the 10 low quality audios, and those will multiplex up to a certain level, and then this is going to be the 2 high quality audios, and then down here there's going to be the 10 megabits per second.
We're still not getting your screen.
Really? Okay. Well, everything probably crashed there. Life couldn't be easier, right? Let me see how I want to approach this. I could pause the video, or I could just simply slide back over to where the web browser is and just see what it thinks is going on. Yeah, sharing went away, so now I'm going back to sharing. And
There it is.
yeah, sharing got clicked off. I mean, in that moment of logging me out and then me having to log back in again. So I've just started to drop here. how I'd look at this is different levels of multiplexing. So we'll multiplex the 10 analogs together, and those 10 analogs are each going to be at 64K. Because we already did that calculation. We have 8 bits per sample. We have to multiply, for Nyquist, we have to multiply 4 kilohertz by 2. So 2 times 4 times 8 is what that number was that we did before. So that's 8 times 8 or 64K. So we got 10 of those. And that's going to be, it's not cooperating with me too well. That's going to be 640 kilobits per second. And then the high quality audio is 20 kilohertz bandwidth. And I'm going to go off and do a side calculation on that one. If you're doing a quiz or a homework problem, you obviously are allowed to do this and expected to do this. So I'm just going to use this Python console to just do the quick calculation. So I'm going to say that with W equals 20 kilohertz, I would like to oversample and have my folding frequency at 24 kilohertz. So my sampling rate is at 48 kilohertz, which is an industry standard in recording. But sometimes in recording, they actually go up even higher. They'll oversample it even higher for higher fidelity and less issues due to filtering. So even though we're starting at 48, I'm just going to run some numbers here. Let's say 48K, which is to handle the bandwidth W. And then we have 24 bits per sample. That's 1152 kilobits per second. But suppose we decided, still wanted to have 24 in there, 24 bits per sample. Suppose we decided to take this up to really high quality studio audio, which would be 196. Just verify that. 48. Other popular sampling rates in high quality audio processing are 2 times 48, which is 96, or 48 times 4, which is 192. It doesn't really matter. For example, I would specify this in a problem, but let's just be really fancy about this and go with the full rate. So I'm going to go with 24 bits per sample, which is also a very, very high bit resolution, the highest quality you could probably go for. And I started off with this being two channels, but now I'm going to raise the rate up to 192. So 9216 is what's needed for that. And then of course this is 10. I keep it in kilohertz, 10,000 K. So now the multiplexer would add all of those streams together. How it interleaves them just depends upon the framing structure that would be established for this link. And when I say framing structure, I'm kind of talking about, in this example, for compact disc, it's just some framing structure where the bits get packed in, and then you have a standard that tells you how you unpack them, or how you pack them, and then how you have to unpack them. So again, I'm going to go do the math over here. So we have, clear that away. So we have 10,000 plus 9216 plus 640. So that's 19 megs, 19.856. So that would be the number in here. Probably can't tell what I wrote there, but I wrote the word overhead. I'm just going to pull a number out of the air. Up to 10% could be spent on overhead. It could be even higher than that, but suppose it is 5% in this case. And that's extra bits, encoding, cyclic redundancy check codes, or parity codes, or other type of encoding might be thrown in. 5% is probably pretty conservative. It's not really pushing it as hard as it could be pushed. So I'm going to multiply that times 1.05, so I get that 5% in there. And now I'm up to 20.8, whatever that number was that just disappeared. 20.848, rounded up to 9. So that just gives you an idea of how a digital multiplexing scheme could be put together for some particular application. Down here, the next example down is the digital telephone hierarchy, and it's called the North American Time Division Multiplexing, which is TDM hierarchy based on a single voice signal that's sampled at 8,000 samples per second and uses a 7-bit quantizer plus 1 signaling bit. So in the case of our telephony standard, which is when we're talking on the phone, and I don't mean using voice over IP, but just standard telephone call on a wired phone, they allocate 8 bits per sample, but only 7 of those go into the quantizer to actually form an estimate of the sample, and then there's 1 bit for signaling. So North American TDM also comes up with 64 kilobits per second, but for a slightly different reason. Then the rest of the hierarchy is kind of described here, where you can have one wire pair is called digital signaling number 0. A T1 is 24 wire pairs, a T1C, and then you can see it just goes up higher and higher. A T5 is 560 megabits per second. And some of you have probably heard these terms before because maybe you work at a company that still uses a feed like this, and this is how much bandwidth they're buying, and sometimes it's listed in terms of the system number, T3 or something like that. Has anybody ever bounced into that or heard people talk about that? Okay, that's fine. That is the end of that chapter. So I'll maybe create a problem like this for the next set as well. I don't think there's any quite like this in the book, but I'll do something. If not, it'll be a mock quiz. It's pretty straightforward though. The only real signal processing comms analysis has to be taken into account is Nyquist. If you're given a bandwidth, then you have to remember to double that bandwidth up to handle sampling theory, and then just remember to multiply everything out. And you could specify an oversampling factor, like it's not good enough to sample at twice the highest frequency, you have to sample at 2.5 times the highest frequency, or 3 times, or some other scaling factor like that. Any questions on this wrap up in chapter 3. Okay, as promised now, well, wait a minute. I do want to do this, but I want to go over and do this example that I started last time in chapter 3. If it will cooperate. It's acting like it doesn't want to respond to me right now. There we go. It's just sitting here though. I almost feel like I've got this thing trying to do too much. What I wanted to come back to is the PCM encoding functions, which is something that you'll be playing with in the second project. So I have these functions, and I talked about them a little bit last time. They're located inside the digital comm module. So you have to load Scikit DSP comm digital comm, and then you have access to PCM encode and PCM decode. So what PCM encode does, and if I hit Shift Tab here, the first argument is just signal samples to be PCM encoded, and then the number of bits of precision to encode those PCM samples to. So it's taking numbers in the array X, which are double precision floats, and it's going to quantize those into signed integer representation, and then serialize those bits that correspond to however many bits per sample, serialize those, and that's what gets returned out of the function. I think that should make sense. It's like an A to D converter that produces a serial output stream, and then PCM decode does the opposite of that. You give it the serial bit stream, and then you tell it how many bits to correspond to each sample, and it assumes that when you're giving it this input of in an array of just bits, zeros and ones, that it assumes that the first n bits correspond to the first sample, the next n bits correspond to the second. So there's no data framing, there's no built-in synchronization or anything which is needed in a real comm system. That has to be supplied by the user. So here I tested with a sinusoid and just looked at the serial bit stream. And then the second example, which I ran last time, I put a channel in here that actually can put noise on each of the serial bits to represent a communications channel in much simplified form, so that I can then drop the signal to noise ratio down and start producing bit errors. But in this case, what I want to do is I want to take that away. I'm going to do 8 bits per sample. Then I'm going to do an error probability test, and it's not done with that yet though. There we go. That's really, really slow. You can see the dot over here is saying that the kernel is busy. It's done. No errors because there's no noise on the system, and we listened to this last time, but I just wanted to emphasize something about this, though, something I didn't show you last time.
The little tales they tell are false. The door was barred, locked, and bolted as well. Ripe pears are fit for a queen's table.
So that's pretty clear sounding. If I was to increase the number of bits per sample, it would get better. But what I want to emphasize now, though, is suppose when I try to play this back or try to go through the decoder operation, I'm going to do something. I'm going to mess things up here on purpose. I'm going to give it one less bit, so I'm going to start at bit 4, and I'm going to stop at 4 bits from the end by putting in the -4. Really, really slow. Oops, I used the wrong notation. I needed to use the colon operator in here. So now I got to start this over again. So what I'm doing is I'm getting the bits scrambled slightly by not framing them into the 8-bit words that they should be framed into. And I'll run it through the bit error detector. And it says there's no bit errors. That's because it doesn't know about the framing operation. It just is looking to find that the same bits came out the channel that went into the channel, and that's true. But in the decoder operation, I've skewed things over, so now when we go to listen to it, and this is so incredibly slow, it's not very responsive at all. Okay, that actually sounds somewhat intelligible because all I've done is shifted over by 4 bits, but the samples are not being framed properly. So if I was to go down here and try to do an overlay plot of just part of the speech segment, we're going to see that the blue trace and the orange trace are nowhere as close to each other. The original audio is in the blue, which is hidden behind the orange, which is all kind of messed up because I don't have the bits ordered properly anymore. I was expecting the least significant bit, and then in each packet of frame of 8 bits, the most significant bit I believe comes last, or it's vice versa. I have to look at the way I wrote the function, but at any rate, just trying to demonstrate that in time division multiplexing and serializing bits, you've got to get the framing correct, otherwise you don't know what you've got, because you have to have a marker to know how to tear it back apart again. That's all I wanted to show on that, so I'm going to get chapter 4 here queued up. I think it's going to be hard to get anything done today. Maybe I have to reboot this system. Maybe it's a combination of the video software running, the one local and then the one that it's allowing me to do the video conferencing, but it's just running really, really slow. Okay, now we'll look at the exam, and what I want to do to start off is just look at the histograms that I created, which are down here. Yeah, it's really, really slow. Okay, so this is, at some point, this will become a histogram that has the convergence of both quizzes and homework. Because I haven't graded any homework yet, and I'll have time, presumably next week, unless something amazing happens, I'll have that merged in here. So in a normal day, a normal semester, I take the quizzes and I take the average of the quizzes, dropping the lowest quiz, and then I take the homework, don't drop the lowest homework, I just take all of that and average it equally. So the quiz average with 50%, with the lowest quiz dropped, gets added to the average of the homework. So each gets weighted 50-50. That's the normal way that I do things. And what I've done here, though, is because there's no homeworks, this just represents what's gone on 3 quizzes. So I'm just wanting to show you where it's at right now. I expect things to be much higher than this when I put the homework in, but I just wanted to let you know where that's at. And the low score is somebody not taking the class for credit. So that, although that skews the mean, I just left it in my spreadsheet. So the high of 83 and the low of 52, well, the low of 51.3 is the lowest bar for those taking it for credit. But like I said, this will slide up considerably, I expect. I expect there will be homework scores that are easily in the 90s. I really do, and you probably do too, you just won't admit it. But so that will change. The second histogram is for the exam. And so here we've got a high of 99, a mean of 78.7, a low of 61. All in all, not too bad. The scores tend to be spread fairly widely, and all the scores are good by me with the exception of one score that's in the 60s. Again, there's a person that's not taking it for credit, so that I'm not worried about. But of those of you that are taking it for credit, there's a score in the 60s that I'm concerned over. So I don't know if this brings up any discussion, but again, I expect this will tighten some after exam 2. And then it's hard to say what will happen on the final. And how is exam 2 going to run? It's going to have to be some honor code based system, and I haven't decided how I'm going to make that happen because we're not allowed to meet as a group, even though this class could perhaps get away with it. In general, it's just not possible right now by the rules. So I'm going to look at the third histogram, and this one is compositing together the quiz scores, not dropping any quizzes, and the exams. Here the mean shifts down, expected because right now the quiz average is low. The homework average will pull that up when that gets merged in there, but the distribution is still similar, not the same. There's a high of 89.9, there's one around 80, and then there's one around 79, and then a few other lower ones in terms of this compositing. And how did I composite this? Well, I composited this by the exam is worth 15%, and homework and quiz averages are worth 20% come the end of the semester. But I think what I did for this, since I didn't have any homework, I said the quizzes alone effectively would count 10%. So there's just a 10% merging from the quizzes and then a 15% merging from exam 1, and then I divide by 0.1 plus 0.18, so that's 0.25. So that's how I get this normalized to 100. Anybody have any questions? If you want to ask individual questions, this will be for after class ends. You can message me on Slack using the direct messaging. So you can direct message me if you want to. If you don't want to share it with the group, then that's fine when it comes to talking about scores and things like that. And I encourage that for anybody that's concerned right now. because the last day to drop is the Friday after spring break, as I'm thinking right now. I think I wrote that on the syllabus, as a matter of fact. Okay, I've got your question, John, but I will have to answer that when class is over with, which I hope is okay, because I don't want to fumble around and take more time. So I could go through the problems and I could see what feedbacks there might be. I don't really want to spend a lot of time on this because we have other things to do today. First problem, well worked by essentially everybody, and pretty much if you got part A right, you got part B right, because it was just taking the Fourier transform. So that was done well. Second problem, getting the fact that the period is 1 over 50, or the period is 50 and the fundamental frequency is 0.02 hertz. That was essentially everybody got that. Applying this theorem in here for periodic signals was some confusion for some of you, and totally not knowing to use it for at least one other person that I'm thinking of. But again, was worked perfectly by a goodly number of people. And in the green box down there is what the equivalent Fourier, what the Fourier coefficient is, because in our modeling that we did, the Fourier coefficient is the combination of 1 over the period times P of f, when f is replaced by the fundamental frequency, and then n is put on top of it, so I can sample P of f at the various harmonics. This one you started asking me about on Tuesday. So here it is. The period is 6 seconds, and that's evidenced by this. I kind of wish somebody would have said, is that y? Because I had letters mixed up on here. If I left it as x, which is the way I thought of it, this should have been changed from y to x. But it didn't appear from the way I graded that had much impact because of other factors that I observed. But if you think otherwise, you can direct message me or send me an email or something. Since I haven't scanned the exams to give them back to you, you may not remember what you did on a particular problem. At any rate, the fundamental concept here is that every time you have a delta function and you can involve it with some other function, namely this impulse response, this property right here is in effect. So it's just a superpositioning of those impulse responses shifted by the pulse train period. And then in terms of getting the power, since this is a power signal, it's periodic, you just have to integrate over one period, the magnitude squared, and divide by the period, which is 2/3 watts, which I think better than 50% had this without incident. This one was also worked really well by most everybody. It was obviously something that you want to work in the frequency domain. One person went at it in the time domain, and it turns into a mess because you've got to convolve two sinc functions together, whereas it's much easier to multiply their Fourier transforms, and that's what I was getting at in here. The filter is band limiting, so it takes the spectrum of the signal and band limits it, because this f over 20 means that the spectrum runs from -10 to +10 hertz, whereas the filter, when you plug in 2W, it runs from -4 hertz to +4 hertz. So it's chopping off the spectrum and band limiting the signal. so it turns into a sync that has got a narrower bandwidth than you start with. So it goes from 20 down to 8 hertz, and I tried to show a picture of that at the bottom of the page. It's still a sync function, but it's more compact. Well, it's less compact. I mean, it's more spread out on the time axis because the bandwidth is narrower. This is just power spectral density of a sinusoid. So you have to remember that the spectral lines are amplitude squared over 4 for each individual sinusoid. And so what I did is I used the trig identity, multiplied cosine times cosine, and got 1/2 of the sum frequency and 1/2 of the difference frequency. So we had 100 kilohertz and 1 megahertz. So we were talking about 1.1 megahertz and 0.9 megahertz as the frequencies. And it's 5 squared, which is 25 divided by 4 is the height of all 4 of the spectral lines. Down in sketching the spectrum after it's gone through an ideal low-pass filter, that's just going to remove the components above 1 megahertz. So that's that picture. Number 5 here is a simplified version of binary phase shift keying. Rather than having an actual pulse train with random bits, this is just a single pulse multiplied times a cosine. So applying the modulation theorem directly, we just get the spectrum shifted up and down in frequency. The pulse width is 0.5 seconds, so the nulls are going to occur at 1 over 0.5, which is 2. But then when you shift that up in frequency, that makes the nulls occur at 2 hertz either side of 10. And if you wanted to think of this as double sideband modulation, which is what the intent was in the problem, the first thing you do is perhaps pre-filter. In this case, that wasn't part of the requirement to show a pre-filter, but I just drew it in there. The pre-filter would, in a real communication system, would be to limit the noise that would get into the front end. But the next step is to multiply by a coherent carrier that's right at 10 hertz. And then that gets you a difference frequency down at 0 hertz. And then I said to set the bandwidth so that it would process the main lobe, which means you need to have the cutoff at 2 hertz. I had more math in here than what I was looking for. And just to make a comment, the hat that I have in here, or circumflex, is not Hilbert transform, but in estimation theory, it's also common that when you send a quantity over a channel, say call it M, the received signal would be a hat, meaning M hat would be the estimate of M. So I'm in the habit of doing that. The Hilbert transform is not as active in my modeling as estimation theory in general would be. Number 6, we talked about some on Tuesday too, and that is finding the normalized message. In this case, you can see by looking at the message itself, because I have 2 minus signs on there, and when t is equal to 0, those 2 cosines constructively combine to have a minimum of -6. And the definition of m sub n of t is m of t over the absolute value of this. So this number is what gets plugged in here. And somebody definitely knew what they were doing because they wrote that nice and clearly on their paper, that is how we form the normalized message. So dividing by 6, so the amplitude and phasing of the message signal is not getting messed up. So you don't divide by -6, you divide by the absolute value -6. And then in order to identify the modulation index, a number of you got things confused in your head as to what you needed to do. The easiest way for me is to work with a normalized message. So when you have a unit amplitude message, one that swings to a negative value of -1, then when you do the factoring in here, like I've got right up in here, you can just say, okay, as long as I factored the 10 out from up above, so I had to factor that out in front, then I can immediately say that is the modulation index, because that's the depth of the modulation. It's going to go 6/10 of the way towards 0 on the negative excursions of the message. Not all the way to 0. If it went all the way to 0, then we would have 1 minus 1, and that would be 100% modulation. So here we have 60% modulation. If you don't like factoring like that, and you just would choose to look at it in this form, you can still arrive at the correct number, but then you have to do more thinking. You have to say pure carrier has an amplitude of 10 inside the square brackets, and what is the peak value of the message? And we know its negative peak was 6, so you'd know that there's a 6 in there, so you can just look at that again and say when the message takes on its negative extreme of -6, we'll have 10 minus 6, so that ratio involves what the modulation depth or modulation level is. So it's, again, 6/10. You could get at it that way. Finding the power in the sidebands was just applying this equation that you've seen before. Everybody had that on their paper, but not everybody utilized it properly. The biggest mistake, if you didn't get A right, I worked with you on part C for using the wrong A, but some of you had problems getting the power in the message calculated correctly. You have to take the peak value of each term of the message and square it and divide by 2, and that's what's done here and here. But then you also have to divide through by the normalizing factor squared, so 6 squared. So I got 125 watts, and the carrier power is 1,250 watts. Advantages of AM and double sideband compared. This is kind of redundant, but I decided to just write it up as if so that you have to get a pro and a con for each. AM, easy to demodulate, inexpensive to demodulate. Not many components are involved. Major disadvantage is lots of transmit power, and very little power ends up in the sidebands in order to maintain a modulation index less than 1. Double sideband, very power efficient. All the power goes into the information sidebands. It's a relatively simple modulator, is what some of you said. Major disadvantage is the complexity. It requires coherent carrier recovery in order to demodulate. This problem, very easy, forming an analytic signal. So there's really not a whole lot I could say about that because most everybody got that right. It's probably one of the easiest problems on the whole exam, I would say. And you had problems similar to that on the homework, so I think that was good because it probably helped you see that immediately. I can take questions on the exam, or I can just move into chapter 4 at this point and get a little bit started on that and then switch over to the project. But does anybody have any questions right now? Type them into Slack or something. Personal matter questions, remember to direct message me, and I'll be working on responding to those after I'm done with the lecture today. So I just want to get a little bit started on angle modulation, and then I'm going to say some things about the project. So at one time, before the current edition of the Zemer and Tranter Communications Theory book, chapter 3 and 4 were all in one. So there was a large chapter. And then in this edition of the book, the material got split in half. So when I say at the top of this page, continuing from chapter 3, it's like you would just be in the same chapter in the previous edition of the book. And I don't know if I ever told you this, but I studied out of this book when it was in the first edition. So I've been around it for a long, long time. So when we were working in chapter 3, we've been focusing on this aspect, the amplitude modulation. Now we're going to switch gears and we're going to spend our time focusing on the phase in the argument of the cosine. So an angle modulated signal takes this form. We consider now this is a constant. And all the information gets poured into the phase of the cosine. So we have terminology that gets talked about actually in Signals and Systems 1, 2610. So these concepts first get defined in there. They're clear in my mind because I think of it as kind of a special introduction for when you later would see it in this class. Instantaneous phase is just taking the argument of the cosine, and at any instant of time, that's the phase of the carrier. Phase deviation is when you separate away the linear phase at the carrier frequency. This is just a linear phase. And then you're left with just the phase deviation. Instantaneous frequency is the derivative of the instantaneous phase, and it's composed of a constant, that's the carrier frequency, or the nominal carrier frequency, and then the derivative of the phase deviation is how the frequency of the carrier is deviating around that constant carrier frequency. So there's two basic forms of modulation, of phase modulation, and they're really can be rolled up into one, but two different classes that ways you can look at it is phase modulation, where the message is applied in terms of the phase deviation and a constant from the modulator that controls how much phase deviates with the message. And Kp is that constant. It has units of radians, say, per volt, if it's a voltage waveform at the modulator. And frequency modulation, or FM. And in frequency modulation, you're looking at the instantaneous frequency deviation, and you're making the message proportional to that through a constant called the frequency deviation constant. And because of this derivative relationship, we can go back to the phase again by integrating both sides and getting the phase deviation as the integral of the frequency modulation, again with our constant Kf. And then to be mathematically sound, there should be an initial phase state that corresponds to where the phase was at some time t0. And the units of Kf are radians per second or radians per second per volt. And when we actually get into looking at a modulator here for FM, we'll actually break Kf down into 2 pi Fd, where Fd is the deviation constant in hertz per unit of m of t. This is one of the first things that goes on in lab number 5, which is in the process of being transformed right now. If you had an analog discovery, though, it has FM modulation capability, and it uses something like this with a constant to set the deviation. Looking at the clock and looking at the time, but knowing that nobody's running to class, maybe, I don't know, if somebody's got a class right after this that they're going to go video into. I'm just going to skim ahead a little bit. Look at this picture. On the left, we see phase modulation with a phase step being applied at t is equal to 0, whereas if we do it as frequency modulation, we see a change in the frequency, a step change in frequency, whereas a step change in phase is different. So you might find that intriguing. We'll study narrowband angle modulation, which looks kind of like AM, where we use a power series expansion and assume the modulation index is small. But in general, we'll be spending a fair amount of time on angle modulated signals that have a sinusoid modulating them. And we'll get at that by doing a Fourier series expansion. And that Fourier series expansion will land us into a Bessel function, which is a special function. It's a solution to Bessel's differential equation, actually. First kind, order n, with argument beta, which Bessel functions show up in electromagnetics and in optics when you've got circular symmetry and you're solving differential equations. This is what the plots of the Bessel functions look like. And if we were to look at the spectrum, which is kind of where I want to stop right now, when you look at the spectrum, a single-sided spectrum of a cosine wave frequency or angle modulating a carrier, we'll get a central component at Fc, and then we get spectral components either side of that at multiples of the modulation frequency, but unlike AM or double sideband, which stop at the first pair of sidebands, FM now, or PM. PM and FM are kind of synonymous with each other. The bandwidth expands way out, and I think I've got some examples in here of a VCO, but I just want to, this thing is very sluggish again. Pretty sure I have a simulation example. Yeah, here's one. This is kind of indicative of FM radio broadcasting, where we've got a deviation constant. The peak deviation of the carrier can swing up by 75 kilohertz and swing down by 75 kilohertz. And then the message bandwidth goes up to around 12 kilohertz maximum. So in this case, I just looked at a 1000 hertz tone, a 1 kilohertz tone with that deviation set up, and you can see that that signal expands the bandwidth out from plus and minus sidebands at 1 kilohertz all the way up to in the neighborhood of 76 kilohertz above and below the carrier frequency. So the thing that should be hitting you is the bandwidth of angle modulation expands upon the modulating signal's bandwidth by a huge factor, and we'll be exploring that, and that is not very conservative of bandwidth, but it gives high fidelity and high quality to the received signal. That's about all I have time for on that. I just now want to jump back over to the project, and if you want more information, you can ask me, or I might decide to make a short video that extends off of this one. Right now, the talking for 75 minutes is making my voice get really scratchy. So what I wanted to talk a little bit about, though, is something that's needed in the area of signal processing to do this project. If I go up into here, there's 3 areas that need special attention. you need to design a low-pass filter to go into this interpolator, and it's running really slow. I can hardly write. Yeah, I didn't even spell it right because I wasn't knowing what letters it was going to eventually put on the screen. So you have to design a low-pass filter for that. Moving further up to look at the block diagram. If this will get into focus, you need to design a bandpass filter to only receive a particular channel. So that bandpass filter is going to say be setting right over the signal of interest in your design. And then you'll need, inside of your coherent demodulator, you need to design another low-pass filter. So you need to do that a couple of different times. And in the discussion down here, I talk about designing the filters and talk about the needs to use an object that I've created in another module of Scikit DSP-Com for doing upsampling, or for doing interpolation and decimation. But behind all of that will be loading up modules that allow you to do FIR filter design and IIR filter design. And then also loading in another module called multi-rate helper, which allows you to do the multi-rate signal processing. And multi-rate sounds pretty sophisticated, but you're going to just kind of use it at a high level in this project. Multi-rate just means you have more than one sampling rate inside of a set of algorithms for a design. And I've got helps for that. At the end of the Jupyter Notebook, there's direct links, or if you're using a PDF viewer that supports links, and the one that I draw on here doesn't, these are links to some added notes for designing these filters. But the idea of designing the interpolator, I'll just take that as an example, and then I'll see if there's any closing questions before I wrap things up. In the design of the interpolator, where you want to upsample by a factor of 12, the objective there is you come in with samples at 8 kilosamples, and then you're going to increase the sampling rate by a factor of 12. And that means you're going to go from 8 kilosamples up to a number you see here, 96 kilosamples. And an upsampler does that, and when you upsample by a factor of 12, you take each sample of the input and follow it by 11 samples of 0, and then you grab another sample of the input, follow it by 11 samples of 0. And what you're doing is you're jumping the sampling rate up through that 0 insertion mechanism, but then you end up getting images in the spectrum, and really what you're having to do is you're having to interpolate samples where all those zeros are, and you would do the interpolation with a low-pass filter. So the low-pass filter needs to be approximately, have cutoff frequency approximately at 4 kilohertz, because that was the usable bandwidth of the input. So you design a low-pass filter around 4 kilohertz. In this case, I designed a low-pass filter around, so its cutoff frequency was 3300 hertz, and its stop band critical frequency was 4300. And I did that over here in the notebook. Let's see, in the project notebook. I started to add this. This isn't in the notebook right now, but it was just taking code that was in that PDF. So I started creating a section here, and I may push this one up here so it gives you some playground area. I said, try out some filter design that's found in the project reader or PDF. So I followed these two links in here and got to notes that are in GitHub or read the docs for the Scikit DSP-Com. So this talks about filter design and the prototypes and everything that are available in that module. And then this second link talks about how to design upsampler or interpolators and decimators, which in the project are exactly what we need. We need an interpolator at the midway point through the Weaver modulator, and then in the coherent demodulator, the receiver, you need a decimator that will then downsample to 12 by 12. And the kind of nice thing about this is this low-pass filter in the demodulator that's sitting in here in the decimator can serve the purpose of the low-pass filter that you ordinarily have in a coherent demodulator. In other words, this low-pass filter will prevent aliasing, and it will also make sure you get rid of the double frequency terms. So just the final shot here is to just see how I went about doing that. I designed the filter right here. I said it should be a Chebyshev type 1 prototype, and the help tells you how that works. There's various examples given in here. And I want the cutoff frequency to be at 3300 Hertz, the stop band critical frequency to be at 4300. This specifies how much ripple in the pass band. This is the stop band attenuation, and then this is the sampling rate. So as soon as I designed that filter, it said, oh, it's going to need to be a 12th order filter, and it outputs either as coefficients for numerator and denominator, difference equation implementation of the filter, or it outputs as a second order section cascade. And I'm going to use the cascade form down below, but I have a function in the IIR filter design helper that you can plug into very easily and get a quick look at what the filter looks like. So in this case, the filter cutoff is very close to 4,000 as we're looking. There's the ripple, and it's very steep skirted filter at this point, just to kind of verify that if I didn't want to have that be so great, but in the application here we want it to be great like that. If I made this push out a lot further, like say, I don't care, it can go all the way out to 6,000. It'll design the filter, then I can look at its plot, and I could have overlaid a plot too. I didn't do that, so let me do that. Just show you how I could do that. SOS, things are so sluggish. I'm going to change this back to what it was. It was 4,300, I think. So this will be order 12. The other one was order 8. So I can just put in here, I can go SOS, tab, and it should show me what's in the workspace already. And now my plot will have a slightly different filter in it because the stop band critical frequency was to be 60 dB down, but now it's moved out in frequency because I said it was okay to go from 4,300 up to 6,000. So these are the types of things you get to play around with. But in this project, you don't really have a lot of tolerance because you need to get down very close to 4,000 because there's going to be a spectral image that's going to leak in if you don't take care of that. I feel like I've got a very much not in control computer, so you need to get this down because there'll be another spectral image sitting right next to it that this filter has to eliminate in the interpolation operation. So that does it. We're well past class time. You haven't yelled at me yet. I haven't gotten any Slack messages, but I can add more to this or just let you read it and then start absorbing it, because if I throw things at you and you haven't read the reader document, it's not going to really mean a whole lot to you. So you need to get into this document and start reading it and then start writing code. So one last minute tip that I guess I can give you is when you have to start writing code, one of the things you're going to need to do, say when you build the Weaver modulator, and that's what we have. Well, let's see. Not in the right section here. Yeah. Here's the spot to build your Weaver modulator. So the types of things you're going to be needing to do just to start processing signals. And if Colton was here, he would probably be asking me this question, because I think he's had it on his mind. See if I can get this thing to roll to that. Okay, so you've got to implement this in the Weaver modulator. One of the things you have to be able to do is take all the signal samples that come in here, and you need to be able to multiply them times a cosine. That cosine will have fs1 equaling 8,000, w is equal to 4,000 in this case, but you'll need to figure out a way to do that. So over here in code, what you want to do is you want to define an index array n. You might call it n1 to correspond to s1, or I mean fs1, and then you'll go something like a range the length of x. So that will be your message that you're modulating, so the length of x. And then you can come down here and you can create a signal. We'll call it x1, and that can be x times the cosine of something or another that's going to be n1 over fs1. So there's going to be an argument in here that's like this argument, 2 pi times w over 2, and then n over fs1. So you're going to be doing array processing. So you're going to use an np array or nd array, and you're going to be forming an array of these cosine samples, and they will get multiplied times this message signal that's coming in. I called it x over here because in my function prototype I've got x up there. X is the input message signal. So that's something I'm just throwing at you, and then you can create an n2 after you upsample, because you'll need to, after you upsample and interpolate, you'll need to have an n2 array over here, because this will be at the upsampled rate. So you'll just create that based on the length of the array that comes out over here. So that happens a ways down the page here, but you are going to have an n2 equals something, a range the length of something else. And just like in the homework problem, I recommend giving names to these things. You know, XA, XB, YA, YB, and I ran out of letters there. I should have started one letter back, but come up with something so that in your code you can keep things straight. I think I'm ready to stop though. I'm ready to actually stop sharing. And then we're back to not seeing my screen and nobody's camera's on. Everybody's still hooked up though. Are you ready to go move off and wrap up the homework? And then I can get the video processing, and I'll start answering any questions that might be popping up on here on Slack. I won't be talking to any of you in person, but have a good spring break wherever you end up sitting around, because I'm not going anywhere. There is a discussion about getting access to the lab, but I don't know what the result of that is right now. That is something that Daniel and I will get to talking to you about if that's going to happen. That started early this morning. Some more paperwork got filed, and it's going to get reviewed by the provost, and I don't know whether it's going to go or not. So, and maybe you don't even want to come to campus, but we'll let you know if something is going to happen. Anybody want to say anything before we sign off? I know John has a microphone available.
No, that's about it for me.
Okay.
Except for that's it.
Okay. Well, I'm going to leave the video conference, and you'll just have to chime in with questions. And like I said, if I get some time here, I'm going to try to use my scanner here at home. It's going to take some time because it's not really designed like the one in the campus is set up, where I can put a big stack in and it will very, very quickly scan it. But that's for me to deal with. Have a good spring break and stay COVID-19 free, and we'll be talking. Bye for now. Copy call data to share. What is that? And where is my call data? Okay, it's not there. I'm not liking this a whole lot.
What?
I'm not liking this a whole lot. Nobody talks to me. And only 3 out of 7 or 8 people were on the call. You remember Andrew Smith? You can't not.
Of course, I remember him.
Well, his brother is in my class.
Yes, you said that.
Yeah. Do you remember him at all? He's not nearly like Andrew, as I'm learning from his exam, and he's not very diligent about. He's pretty smart, but he's kind of not engaged that much.